Now, on Monday, for section 12.1, as a recap, we talked about arithmetic sequences and series, which meant, you just have a list of numbers, and to get from one number to the next, you either add a constant value or subtract a constant value, which was called a common difference, and that's how you make your list. On Tuesday, you watched a video on 12.2, which dealt with geometric sequences and series, which is the same idea, it's just a list of numbers, except you multiply the previous term by something to get to the next term. So instead of having a common difference between your terms, you have a common ratio between your terms. Today, what we're going to talk about is infinite sequences and series. So mostly geometric, that are going to be the type that we deal with. But we're going to talk about, okay, what happens when it literally never ends? Like, not only are we talking about the first 100 terms, but we're talking about something that never, ever, ever ends at all. E is kind of an example of an infinite series. If you recall, when we talked, you don't need to write this down, but when we learned about E, we said E was 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 plus etc. And that went on forever. Now, if you actually add these up, this is going to be 1 plus 1 plus 1 plus 1/2. Oh, sorry, the box is in the way. It's okay, I'll move it. Can y'all see it now? Plus 1 over 1 times 2 times 3 is 6. And then if you actually add these guys together, that's where you get the actual decimal for E, which is about 2.71828. And we'll talk more about decimals and fractions a little bit later. But that's an example of something that you've actually seen already and actually being able to add it up. Now, it's infinitely long. It never ends because that pattern will continue forever. But when we add it, we can pretty much get a very close approximation to it. So I want you to consider this sequence. Let's just actually leave it as the number 1. Okay, so start with number 1. Then your next term is 1/2. Then your next term is 1/3. Then your next term is 1/4. And then this continues for eternity to your next term all the way to 1 over n, where n is just any integer. So like this would be a sub 1. This is your first term. This is your second term. This is your third term. This is your fourth term. And this is your nth term, which, even though it looks like it ends, this is going to continue on forever, because if I tell you that n is getting closer to infinity, then it's never going to end. So as n increases, if you look at this list here, the terms approach, or in other words, get closer to what number? So like 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1 over 100, 1 over 1 million. What are those numbers getting closer to? 0. 1 divided by any huge number is 0. So in this case, 0 is called the limit of the terms. So this is the first big takeaway from today. It's written like this. LIM for limit, as n approaches infinity, of this sequence. Instead of like listing out all the numbers, I can just write it as this expression, right? 1 over n. And again, it starts with the first term, second term, third term, goes all the way up to infinity, equals 0. So if that sequence of numbers increases, I'm going to approach 0. I will never get close to 0. I'm just going to approach it, right? These numbers are going to keep getting smaller and smaller and smaller and smaller. The way that you say this, kind of like how we learned how to say log base b of a equals x or whatever, or f of x. This mathematical notation, if you see this, you would read it as the limit of your expression, 1 over n, as n approaches infinity, as n approaches infinity, equals 0. The limit of 1 over n as n approaches infinity equals 0. So you kind of read a little bit ahead and then you come back to n approaches infinity. What does this sound familiar to? Like approaching something but never actually getting there. Yeah, and you guys are very familiar with asymptotes at this point. And visually, that's what we're dealing with, is asymptotes. Algebraically, these numbers are just getting closer and closer and closer and closer and closer, but it'll never actually touch it. So it's the same idea. So this is the first big takeaway. The limit of 1 over n is equal to 0. 1 over any big number as n approaches infinity is going to equal 0. Now, later on in calculus, you can take the limit as n approaches anything. So I can look at a graph or a sequence and I say, okay, what is the limit as n approaches 5? And then those numbers are going to converge to a particular other limit. It's not necessarily going to go into infinity forever. But again, we're not touching that. This is a very, very in-depth calculus concepts that we're literally just like getting our feet wet with. Okay, so we're going to talk about some theorems for limits. And I want you to suppose that the limit of, and sometimes I write it or I say it backwards just because I write it this way. The limit as n approaches infinity. My infinities kind of look like 8s. Sorry about it. That's better. Of a sub n, so a list of numbers. I'm going to call that limit a. And we're going to do the same thing with b. If I have a different sequence and I say, okay, the limit as n approaches infinity of b sub n, a different list of numbers, and I'm going to call that limit equal to b. This is just going to prevent us from writing out the limits over and over and over and over and over again. And similar to like your exponent and your logarithm rules, we have theorems for limits. Here they are. Your sum theorem says, if you have the limit, as n approaches infinity, of a sub n plus b sub n, essentially what all of these terms allow you to do is break apart each of your terms and take the limit of them separately. So this is the same thing as the limit, as n approaches infinity, of a sub n plus the limit of as n approaches infinity of b sub n, which again, I'm shorthanding so we don't have to write all of that as just a plus b. So you just take the limits of each of these terms individually and add them together. For the difference, the limit as n approaches infinity of a sub n minus b sub n, you could probably guess is the same idea. You take the limit of each of those sequences and you subtract them, a minus b. What? Smart. Did you say you feel smart?
Oh. You're smart, Miss Monnier.
Oh. All right, thanks. We can do the same thing for products. The limit as n approaches infinity of a sub n times b sub n is going to equal the limit of each of those sequences separately multiplied times each other, which would be a times b. Quotient, limit as n approaches infinity of a sub n over b sub n is equal to the limit of each of those divided by each other. And then the last one I'm going to argue is the most important one that we're going to use all of them, but the one that's going to be most meaningful to us, I think, is the constant, which is this. The limit as n approaches infinity of c sub n So over here, let me scroll up. I'm going to scroll back down. When I gave you this list, n was increasing, and we divided by a really, really, really big number, which got us closer and closer to 0. If my list of numbers is just a constant, like here's my list of numbers, 2, 2, 2, 2, 2, and it goes on forever, what is my list approaching? I heard something. Did somebody actually say it, though? If you were to predict this number way over here, what would it be? Yeah. So the limit of a constant is a constant. Because there is no value for n that you're even trying to substitute in for. Okay, if you want to see this like expanded, like not, I did the short version so that you didn't have to keep writing the limit all over again and again and again. If you look on your textbook, page 776, they have this same chart on there with like all the limits actually written out. But this is the basic idea. Okay, so here's what I want you to remember. 2 big takeaways. The things that we know for sure. The first, all of these operational theorems, you're just going to use these to break up your expressions, okay, into smaller numbers. The other 2 things that we know for sure is that the limit as n approaches infinity of 1 over n, we know that that limit is 0. And that works if n also has any exponent. If I have 1 over, let's do this. Limit as n approaches infinity of 1 over n squared. So as n gets bigger and bigger and bigger, and I square that, what am I approaching? So like, let me back up. This first expression, 1 over n, we said, okay, my first term would be like 1 over 1. My second one would be 1 over 2, 1 over 3, 1 over 4. And you guys told me earlier, this ends up being like 1 over infinity, which is going to eventually get to 0. Well, what happens if we square n? The first term will be 1 over 1. What will the second term be? Thank you, Xavier. And then the next one will be 1 over 9, 3 squared, right? And then 1 over 4 squared is 16. What are these approaching?
Square numbers.
Well, they're square numbers, but if I keep going, how can I predict what will my last number be? 0. So the point is, no matter what the exponent is in the denominator on n, the limit will always be equal to 0. So that works for n to the 3rd power, n to the 4th power, n to the 32nd power. 1 over n to any power will always approach 0. Some will get there faster, right? But they will always approach 0. Okay, and then secondly, the other one is that the limit of n, or the limit as n approaches infinity of a constant is equal to a constant. And that was like the list earlier that I showed you. If I give you 2, 2, 2, if I predict this term way over here, it would be 2. Okay, so here are the 2 big takeaways. The limit of 1 over n is 0, and the limit of a constant is the constant itself. We're going to use those to find the limits of other sequences. Now, instead of actually just listing out the sequences, though, I'm going to give you a rule for the sequence. So which is just going to look like an equation. So the first one, the limit as n approaches infinity of 1 plus 3n squared all over n squared.
Why is it necessary to write limit?
Because I'm not just talking about this is the question. The question is, what is the limit as n approaches infinity of this expression? Like, I'm not asking you what the expression is. If I didn't write this, and I said, okay, what is this equal to? Then you could actually give me the sequence. A sub 1 would be like if I plugged in 0. So if I plugged in 0, what would that be? Just 1, right? 1 plus 3 times 0 squared over 0. Well, no, that's undefined because you can't divide by 0. So if we plug in 1, that would be 4. If I plug in 2, 2 squared is 4 times 3 is 12, plus 1 is 13 over 4, right? That's how you would generate the list, is actually plugging in numbers. I'm not asking about the list. My question is, as my list increases, what number is it approaching? Okay, so that's why you're actually going to write the limit. What is the limit as n approaches infinity? As my list gets bigger and bigger of the list created by this expression. Now, you could write out those numbers, but sometimes it might be a little bit more difficult to see. I'm going to tell you here that the limit is not 0 every single time. So that's where things get a little bit tricky. So here's what you're going to do. You know the limit of 1 over n, or 1 over some form of n, and you know the limits of constants. So one of the strategies you're going to use is to break up or rewrite your division like this. The limit as n approaches infinity. If I can rewrite this fraction into two fractions to be 1 over n squared plus 3n squared over n squared. And then you're going to start using your theorems, which allow you to break up the limit when you add two different numbers. Okay, so let's simplify a little bit first. This is the limit as n approaches infinity of. There's nothing to simplify with 1 over n squared, so we're going to leave that alone. 3n squared over n squared, what is that? It's just 3, right? And then now if you use one of the theorems that we talked about, this is the same thing as taking the limit as n approaches infinity of the first term plus the limit as n approaches infinity of the second term. Now, this is going to seem kind of long and arduous, but we're not, as you get better, you don't have to write every single little step. So what is the limit as n approaches infinity of 1 over n squared? 0, right? This is one of these examples up here that we just talked about when I circled in green. 1 over n to any power will converge to 0. So the limit of that one is 0, plus what is the limit as n approaches infinity of 3? Did someone say it? 3. It's the constant itself, which means the limit of the entire expression is actually 3. And that's something you probably wouldn't see if you tried to just write a bunch of numbers in the sequence. That would be really difficult to tell. So that's why these limit theorems are actually helpful. No, you don't. I mean, you're going to have to in a minute, but not yet. And you could shorthand it too if you're lazy. All right, so let's do a couple more like this. Number 2. The limit as n approaches infinity of 4n squared minus n plus 3 over n squared plus 1. So again, I could say, all right, guys, make your, write out terms of your sequence and find the limit. Figure out what numbers it approaches. But that's going to be really difficult. You also cannot do what we just did in the last problem, where you split up your denominator because it's a binomial. So another tactic that you're going to use is to multiply by 1 over n that has the highest degree. So our highest degree is 2. So 1 over n squared divided by 1 over n squared. Can you tell me, what does this red term equal? What is 1 over n squared divided by 1 over n squared?
1.
Yes. So anytime I multiply something by the number 1, I'm not changing its value. We're not just like changing the equation or the expression and all. We're just going to make it look a little bit different. Okay, so then you're going to distribute that 1 over n squared to every single one of your terms. In short, what we're doing, and you could write this down if you want, is the idea is that we're going to divide every term by a variable of highest degree. Right? Because when you multiply by a fraction like this, you are just dividing by, because 1 is in the numerator, you are just dividing every term by n squared. Okay, so then this is going to equal the limit as n approaches infinity of, I'm going to divide all these terms by n squared. 4n squared divided by n squared minus n divided by n squared plus 3 divided by n squared all over n squared divided by n squared plus 1 divided by n squared. Okay, so all I did was distribute those fractions there. No, she's playing.
Playing?
Yes, my husband, that's her play with me.
Yeah, that's what
Okay, so then we're going to go ahead and simplify these terms. Do I need to slow down?
He's blinking so we don't have time to write.
I know, sorry. Tell me to slow down when I need to.
I think you just get really excited. Almost like you love the teacher.
Was that sarcasm? All right, are we good? All I'm doing on this next step is reducing. Okay, so 4n squared over n squared is just 4 minus what is n over n squared? 1 over n plus what is 3 over n squared? Nothing, right? There's nothing more you can simplify. All divided by n squared over n squared is 1 plus there's nothing else to do with 1 over n squared. Now, if you think back, the two things that I highlighted in green earlier was that we know how to take limits of constants and we know how to take limits of 1 over n of some sort. So all of these values are fine except 3 over n squared. Is there a way that I can write 3 over n squared to separate the constant from the n squared? Can I write that as, instead of 3 over n squared, as 3 times 1 over n squared? Yeah. Okay. If I do that, now I have either constant terms or I have terms of 1 over n. Okay, so when that happens, I can now go ahead and take the limit of every single term. Now, we're not going to write out, okay, what is the limit as n approaches infinity of 4? The limit as n approaches infinity of 1 over n. We're just going to take the limits of each of them. And so, guys, once you take the limit, you do not need to write this limit as n approaches infinity anymore. Okay, so what is the limit of 4? 4. Minus, what is the limit of 1 over n? 0. Plus, what is the limit of 3? 3 times, what is the limit of 1 over n squared? Okay. All divided by the limit of 1 is 1, plus the limit of 1 over n squared is 0. If I simplify this expression, 3 times 0 is 0, so then I get 4 minus 0 over 1 plus 0. 4 divided by 1 is 4. So the limit of that initial expression is just 4. Does that make some sort of sense to you? Yeah. Okay, not too bad. I do have another example, but for the sake of time, I'm going to skip over that one type of example, and we're going to talk about what happens when limits do not exist. Here's the other thing I want to talk about, though. I want you to notice what does 4 have to do with the initial expression? What does 4 have to do with the initial expression? It's not only the largest coefficient, you were true about that, but there it is. Okay, so the coefficient of your highest degree. Do y'all remember when we graphed these rationals? And we said that in order for you to find the horizontal asymptote, you compare the coefficients of the largest exponent and you divide. If they're the same, you divide them. Well, 4 divided by 1 is 4. And look up here. At the first example, your coefficients that matched were n squared, which was 3 divided by 1, and that limit was 3. Now, they're not all going to be that easy, which is why we have to learn about limits, because there are situations where that doesn't work, but that's just a quick way for you to check what the answer should be as you go through and do all the limit rules. Okay, if the coefficients match, then you divide, if the biggest degree exponent matches, then you divide its leading coefficients. Okay, now we're going to talk about when the limits do not exist. So this is this little paragraph here. You can shorthand it if you'd like. And I guess you can not necessarily have to write that first sentence, but you do need to start with this part. If the absolute value of a sequence becomes arbitrarily great, or if the terms do not approach a single value, then the sequence has no limits. That is the important stuff. Kind of. We have 2 more examples. But that's the last thing you're writing. If the absolute value of a sequence becomes arbitrarily great, or if the terms do not approach a single value, then the sequence has no limits. And we're going to do an example of each of these scenarios where you're going to break up all of your numbers, and when you try to take the limit of some of your values, you're going to see what I'm talking about. You're not really going to be able to. What's up, Kevin? Arbitrarily means we don't know exactly what number they are, but it's just going to be, it continues getting bigger and bigger and bigger. So if you want to write that in that way, if the absolute value becomes, all right, let me write this in normal fit terms. If the absolute value of a sequence becomes really high, that is super basic, potentially inappropriate if you're thinking about it that way, but that's another way of thinking about it. If the absolute value becomes really high, or if the terms do not approach a single value, then the sequence has no limits. So I want you to start thinking about this next example. The limits as n approaches infinity of 4n squared minus 6 over 3n. And we're going to use some of the same tactics as we did on those earlier problems to break up this fraction to find the limit of each of the individual terms. So again, we know limits of constants and 1 over n squares, or n to any kind of exponent. But let's go ahead and divide, split up our terms. Bless you. So we'll say, okay, this is the same thing as the limit as n approaches infinity of 4n squared over 3n minus 6 over 3n. And then we can simplify that, right? This will be the limit as n approaches infinity. 4n squared over 3n. One of those n's cancel, leaving us with 4/3 n, or 4n over 3.
If the limit is 0, does that mean it doesn't?
No, then that means the limit is 0. 0 is an actual number. Minus 6 divided by 3 is 2 over n. So again, we know limits of constants and 1 over a number. So can I rewrite 2 over n as a constant instead? So can we write this as 2 times 1 over n? Okay. So now let's actually take the limit. What is the limit of 4/3? It's just 4/3. What is the limit of n as n approaches infinity? Think about that for a second. As n approaches infinity, what happens to n? Think about what I just said. Yeah, as n approaches infinity, this n will also approach infinity. Now, infinity is not a real number, but what happens is that n is getting bigger and bigger and bigger and bigger and bigger. Minus the limit of 2 is 2, the limit of 1 over n is 0. So that term disappears, but this is the issue. This is the issue of it getting really, really high or arbitrarily great. This limit has no bounds. It's just going to continue. Our numbers are just going to continue to grow and grow and grow and grow and grow. Numbers continue to grow very high or arbitrarily great. Therefore, the limit does not exist. Does that make sense? Okay, so there's one example. A different type of example is if I give you the limit as n approaches infinity of -1 to the n power times n to the 4th power. Actually, let's do this. -1 to the n power times n squared. Now, we haven't had one like this, right? Where the exponent is actually the variable. So I want us to actually write out some numbers in this sequence. So if we start with 0, if the first term is 0, what would this be? What is -1 to the 0 power? What is anything to the 0 power?
1.
And then n squared, that would be 0 squared, so that your first term would just be 0. Okay, so then if I plug in 1, so that's if n equals 0. If n equals 1, which, let me actually just do it like this. This is a sub 0, a sub 1. If I plug in 1, what is -1 to the first power? I'm going to assume somebody said -1. And then -1 times 1 squared is going to be -1. Then if I plug in 2, -1 squared, -1 in parentheses squared is going to be a +1. And then that +1 times 2 squared is 4 will be +4. And then if I plug in 3, what is -1 cubed? -1 times 3 squared is 9 is going to be -9. And then you can kind of have to figure out the pattern now. What's the next number going to be? A sub 4. If you plug in 4, your squared number is going to be 16. And then -1 to the 4th power is going to be a positive number. So you can see what's going on here. I've got patterns of square numbers, but every other number is positive and negative, right? In short, when n is odd, then -1 to the n power, so all of my odd a values, a sub 1, a sub 3, I end up with a negative value. 1 is negative, right? Because -1 to any negative exponent, I end up with a negative value. When, why aren't you writing, pen? When n is even, then -1 to the n power, oh my gosh, is positive. So it's in this case where you flip-flop from a negative number to a positive number that the limit cannot exist which you just put D and E for does not exist. Because if you keep flipping back and forth between positive and negative numbers, then it can never approach just one value. Does that? Yes, -1 to the n power is positive. Does that make sense? Okay, so big takeaways from today. The limit as n approaches infinity of 1 over n, and this goes for 1 over n squared, 1 over n to the 4th power, 1 over n to the 5th power, that number will continue to get really, really, really close to 0. Other big takeaway from today, the limit as n approaches infinity of any constant number, a list of just that number repeated over and over and over again, is that constant itself. If you can remember these two things, then you're in good shape. As far as when the limit does not exist, you're going to get one of these two options for now. You're either going to flip-flop back and forth between a positive and negative number, so you will never approach a single value, or you end up with like n hanging out by itself, which if n is approaching infinity, then that number gets arbitrarily high and continues to grow, and you will never actually approach one single value.